Hi everybody and welcome back to Digital VLSI Design. I'm Professor Adam Teman of the EnICS Labs at Bar-Ilan University, and today we'll be going over the Kahoot for Lecture 8, Clock Tree Synthesis. So our first question is, why not just route the clock net to all sequential elements just like any other net? Because it will create clock skew, because it will cause signal integrity noise hazards, because the load of the driver will be huge, or all of the above. And I believe it'll be all of the above. So let's go and take a look at why. Well, the question is, why not just route the clock net to all sequential elements just like any other net? So we have this pin that comes into our macro, or we have a clock, source that comes into our chip. Often this will be a PLL or something like that that distributes the clock at a high frequency to the entire chip. And this is a net that virtually, during synthesis and so forth, it is connected to a lot of flops. And these can be thousands, hundreds of thousands, millions of flops. And that's really complicated. We have this one net with really high fan out, and therefore it has implications in timing, power, area, signal integrity, and etc., as we went over in the lecture and we'll be going over in the rest of this Kahoot. So let's go to question 2. Which of the following does not cause clock skew? A different number of buffers in the clock path to the registers, temperature variation across the chip, variation in clock period of the PLL, or variation in wire length on path to different clock pins. So I think it's going to be this one. With that, let's go back over to the slides, and we'll see that when we talk about implications on timing, one of the things we talked about was skew and jitter. And this is kind of a schematic of how our clock tree is going to look like. So we have our clock generator. It could be, again, external. It could be a PLL. It could also just be a pin that enters our block that we're working on if the clock is generated outside somewhere else on the chip. Anyway, that's going to go through some sort of a central clock driver, which is going to be, some sort of buffer tree to drive, a large load. And then we're going to branch off into a tree, which is our clock distribution network. Okay, and in any case, what happens is that this part here is common to all of the clock sinks. All of these registers, they have this part within them, so they're not going to be really the skew is not going to have anything to do with them, but they are going to be susceptible to jitter. On the other hand, once we branch off into different branches over here, everything changes. So the length of the wire is going to change, the number of buffers that we're going to have until we reach the actual clock, the clock pin of our flip-flop, variation, temperature, process variation, voltage in this area that we're going to go through these different buffers and so forth. So everything really is going to change along the way and cause skew between two different registers in the design. So question 3, what are the goals of classic CTS? Minimizing skew, meeting target insertion delay, not violating any clock DRVs, or all of the above. And I think that's going to be all of the above. So again, we'll go back to where we talk about it in the slides. And the clock routing problem is that we have a source and it has n sinks, and n can be very big. And what we want to do is connect all the sinks to the source by an interconnect network that's going to minimize the clock skew, going to minimize the delay, the insertion delay from the clock to the flip-flops. It's going to minimize the total wire length and the noise and coupling effect between the different, the nets over here and the signals in the design. Okay, that's going to be really challenging. We're going to have to synchronize this crazy type of thing, and that's why we're going to use a clock tree or the different other approaches we use. When we usually discuss how we do clock tree synthesis, our goal that we always focus on is to minimize skew. So the basic assumption is that during synthesis and during placement, timing optimization post-placement, what we did is we had an ideal clock, and we tried to meet setup constraints. We tried to meet the target frequency or the highest frequency possible by optimizing, upsizing things and changing our logic and so forth, everything we discussed in previous lectures. Now we come and we build this clock tree, and it changes everything because it introduces skew. Not only that, it can also cause hold violations. We didn't have any hold violations basically before. We didn't even check hold usually during the first stage of the design because it was irrelevant without having a clock. But once we introduce skew, then we have that those deltas in our setup in our max and minimum delay equations, and they're going to cause us setup and hold violations. So the assumption is that if we can reduce that delta to be 0, then we'll just meet the timing just as we met it post synthesis, post placement, etc. So that is our real goal. We're going to minimize the skew in order to continue with the meeting the max and min delays as we met them before. But there are some constraints, and the constraints are that we have to have some sort of a maximum transition, load cap, fan out, and maybe a maximum number of buffer levels that we want to have on our clock tree. We also want to meet some sort of target insertion delay often, however, depending on the number of flops we're going to have to have a longer insertion delay. We're going to have more buffer levels. It's not something we can really do anything about. We just probably want to keep it within some sort of reasonable number in order not to cause skew with between our block and other blocks maybe in the design. And also because the longer the insertion delay is, the more variation and the more noise and so forth we can have along the way, and that's not going to be good for us. But really our main constraints are minimizing skew and really meeting these DRVs over here. So that being the answer, minimizing skew, meeting target insertion delay, and not violating any clock DRVs are the answers that we have for the goals of classic CTS. So question number 4, what is not a design rule violation in a novice? Maximum transition at the output of a gate, maximum capacitance, the wire load of a net, maximum fan out of a certain gate, or maximum fan in of a certain gate. And this is actually a question that we had before during our STA lecture, and we saw that the answer was max fan in. Now, why is it that I brought this back up? And as we saw that we have in our SDC, these types of commands, set max transition, set max capacitance, and set max fan out. And what we said about with regular logic is that we're going to have our max and our min transition have to be such that we fall inside the tables that we have in our libraries, in our libs. Same with maximum and minimum capacitance. And actually, these are defined inside our libs, inside our libraries, because the tables are usually common for all the cells, and we want to make sure that the library was characterized from some minimum point to some maximum point, and we have our models defined inside there. So we never want to violate the maximum transition of the lib, though we can override these, hopefully making it harder to meet rather than easier. Maximum fan out is just kind of a nice to have thing that kind of helps us with our meeting our max capacitance and max transition violations. However, when we talk about clock tree, we have another set of these types of DRVs. We have actual max transition, max capacitance, max fan out, maybe max insertion delay and so forth, that are defined for the clock nets, and they're probably going to be harsher than the ones for the signal nets. They're going to be taken into consideration during the clock tree synthesis, not during static timing analysis. So they're a different set of commands, but they're the same types of DRVs. So max fan in, of course, is not a DRV. It's just a trait of a gate, and usually gates in a CMOS library are not going to have a fan in above 4. So question number 5: what is the main benefit of implementing a clock grid or a clock mesh? It results in lower power consumption than a clock tree. It results in lower skew than a clock tree. The PLL design is much more simple than when using a clock tree, or it uses less routing than a clock tree. And the answer, of course, is that it results in lower skew than a clock tree. So let's go and remember what our mesh was. So a clock grid or a mesh is something like this. We have a mesh of wires that goes over our whole design. Lots of these big fat wires. They probably will even take up pretty much a whole meta layer, maybe 2 if we have maybe something like that. And this is going to be a huge wire with huge capacitance, and therefore we're going to need a real big driver to drive it. Not only that, we're going to want to distribute the driver such that it doesn't touch here like in this two-dimensional picture, but actually each of these final stage buffers are at a different little point here across the grid. So we actually have really the same skew, the same time. We have an equipotential at every single point spatially in our design. And then we can just come and hang off flip-flops from that. The extra capacitance of the flip-flop is negligible next to the capacitance of the whole wire, and therefore we can assume that we get our clock to these flip-flops at really an equivalent time. And that's really nice. It gives us a minimum type of skew, and it was used in processors like the DEC Alpha to really get high quality skew, a high quality clock. However, the problem is that these wires are really big, and we're filling them up and discharging them at the clock frequency, and we also have this big huge buffer that's going to be driving them. We saw that there were just crazy sized buffers in the DEC Alphas, and that is wasting a lot of power and a lot of resources, both for placing these huge buffers and especially for taking up our routing resources of a metal layer. So that's why it's pretty much not used in today's SoCs, at least not in its classic way of just covering the whole chip with a big clock grade. So going back, it results in lower power consumption than a clock tree. That's for sure not true. It's more power consumption. It results in lower skew than a clock tree. That's what we said is the reason that we would use a clock mesh. The PLL design is more simple than when using a clock tree. No, it's the same type of a PLL, or it uses less routing than a clock tree. And no, it probably uses a lot more routing than a clock tree. It's going to use at least a whole, metal layer. So question number 6, which of the following is an implicit stop pin or a clock sync? The D input of a flip-flop, the clock input of an SRAM, the A input of a clock buffer, or the clock input of an integrated clock gate. Let me let you think about that for a moment. This is an implicit stop pin. It's a clock sync that the tool will know about by itself. Well, it's going to be a clock input of an SRAM. Now, why is that? So, a stop pin, at least according to the CC-opt type of definitions, the cadence type of definition in their newer versions of their tools, is basically a clock sync. It's where we stop building the clock network. What happens with a clock network is that we define the source of the clock network. Somewhere over here we define a clock tree or something like that. And then the tool goes and looks at the net list and sees what it has along the clock tree. And it continues going and it sees a buffer over here, for example. A buffer is not something that stops the clock tree. The clock tree should propagate it through it. So actually the input of the buffer is some sort of like a through pin. But once it reaches a flip-flop, that's where it should stop recognizing the nets that it's on as a clock net. So this wire and this wire, which have different names, so this might be, clock net 1 and this might be clock net 2 or something like that. They're not necessarily called, the same thing as we called the clock in the SDC or what the original name of the wire that comes out of the port is. But they are both part of the clock net, and we should, deal with them in CTS, and we should route them according to the constraints, the DRVs on the clock tree. However, once we reach the clock pin over here, this is recognized as an implicit stop pin. It knows that this is a clock sync, and therefore what comes out of it, the Q that comes out of the output of this flip-flop is not going to be considered a clock net. It's going to be considered a signal net. And that's one thing. The other thing is it's going to take this pin and add it to the list of pins that need to be skew balanced. So those are implicit stop pins. You can also define a stop pin. Let's say for some reason we want to not go through this buffer over here, so we can define its A pin as a stop pin, and then the clock tree will go up till this point and skew balance this with all the rest of the flip-flops in the design. So we do that with, in Innovus stylus type commands. We do it with a setDB pin, tell the name of the pin over here, CTS sync type stop, and that'll be to say don't propagate beyond this point and add this to the list of syncs that should be skew balanced. There are reasons to do these types of things. Actually, the clock network is one of the most important things at the architectural level in a chip when you're going from the design of the chip to physical implementation. It gets complicated and it's very, very particular per each chip and each macro. One of the things that I always tell the backend guys to do is first things first, bring a picture of the clock tree, a nice schematic block diagram of what you have on the clock tree. You have to look at it, understand what you want to skew balance, what you don't want to skew balance. Are there any things that you want to ignore, or so forth and so on? And by that, build your definitions for your clock tree synthesis for it. It's really important, or else you're going to run into all kinds of hold violations, especially at later on stages, or a really bad and ugly clock tree. So I'm not going to go too deep into it during this course, how to build clock trees for specific designs, because it really does change for each design, and it gets pretty complex when you go down the road. But you have a whole bunch of these types of commands, which we'll see a bunch more in a minute, but stop, ignore, and exclude, and so forth pins, that you're going to actually have to look at your block diagram of your design, find the actual gate that you want to define differently, a stop pin or ignore pin or whatever, and then go and add it and make sure it was actually caught by the command that you ran, and check your clock tree after creating it that it did take into account what you wanted it to do, and it works that way. That's a really important thing to do during backend design. So number 7, what is an ignore pin? And note, all answers relate to pins on a clock net. Okay, is it a leaf of a clock tree? A pin that will be buffered to but not considered for skew? A pin that will be completely ignored and not buffered to? Or a pin that the clock will propagate through without stopping? Okay, and I believe that it's this one. Now, that's a pretty tough one, and probably what you should do is go into the documentation of your tool before you need to understand these things, because they are different between the tools, and there are little details here. But again, what we had here now was our clock source here, and the graph that goes down through the net list and finds where the clock sinks are. But sometimes there's one of the pins here that really causes everything to be to have large skew and to cause lots of problems. For example, in this example I gave over here, we have an output. So we have from the clock source, we are going to the output, maybe to pass the clock signal to a different macro or something like that. And this really has no logic on it, and we can really send the clock directly out there. But what happens is, if this was a stop pin, because this is the end of the design, it doesn't continue, this is the edge of the macro, then we would be balancing this point with all of these points. And that would be something that is really bad to do, because it would cause us to put a whole bunch of buffers over here to make sure that the delay is the same as the delay of these guys. This happens in many cases. For example, if you have a clock divider or something like that, let's say this was the input to a clock divider, and the clock divider was going to go and feed a whole bunch of other flip-flops, then we would want to ignore the point over there and not let the design propagate through it and actually skew balance all of the flops that are on the divided clock with these guys over here, because it will just take the whole clock tree and move it really, really deep. So that is an ignore pin. What it will do, though, it will treat the net over here like a clock net, and it will buffer it and make sure it meets the DRVs. And that's kind of an important thing, because if we use an exclude pin, it won't even treat this net as a clock net, and it will just be a standard signal net, and it won't buffer them in the way that we would want on a clock tree. So, but for an ignore pin, it does. Okay, so is it a leaf of a clock tree? No, the leaf of the clock tree is a sync or a stop pin, a pin that will be completely ignored and not buffered to. That's an exclude pin, in at least in the CC-op nomenclature. A pin that the clock will propagate through without stopping. That's a through pin in the CC-op nomenclature, and a pin that will be buffered to but not considered for skew. That's the correct answer. Okay, so question number 8. The insertion delay inside an SRAM is 100 picoseconds. How do I skew balance it? And here we have a nice picture of what we're talking about. Do I use this setDB pin mem clock skew balance minus 100 picoseconds, setDB pin mem clock float pin minus 100 picoseconds, setDB pin mem clock CTS pin insertion delay 100 picoseconds, or setDB inst mem insertion delay 100 picoseconds? And again, this is kind of hard, and it's very specific to the cadence tools with the CC-op commands. This is the correct answer, and let's go and look at that. So what is the case over here? We have this memory, and the memory actually has a clock tree inside, or it could be any other type of a block. Okay, so there is some sort of a clock tree. There's a delay from over here till we actually use the pins. It could be also a hierarchical block of digital logic that we see inside the top level of the design, but we know that there's an insertion delay from where the pin enters this macro until it gets to where it's actually used. And so therefore, if we were to treat this as a stop pin, a standard stop pin, then it would be skew balanced with these guys. And if we're looking at the insertion delay from here going down, what would happen is that this block would be way down here, and we'd get this big skew between these flops and these sampling points that are inside the clock over here. So what we want to do is we want to tell the tool, listen, skew balance to this point, but skew balance it at some earlier point. X in this case, and this is the the positive direction of our command. So what we're going to do is we're going to call this an insertion delay pin in the Cadence CCOP tool. So it's called .cts pin insertion delay, and we're going to give it a positive number. That means, listen, skew balance this 150 seconds before, so picoseconds before. So we're going to have this be 150 picoseconds before the point where we skew balance all of these guys. In Synopsys tools, it's called a float pin. So you might, again, you're going to have to look in the documentation of whatever tool you're using and really understand how to do this. But this is an important point that you need to know how to do. Take the documentation of whatever your block is, or talk to the designer of the block, see what the internal insertion delay is, and make sure that you add a float pin so it will be skew balanced way before it gets to these guys, or else you're going to have timing problems usually. Okay. So with that, we'll go to question number 9. What is the thing that matters when building a clock tree? And I love this picture. We have over here the things that matter, and here's the thing that you can control. But the question is, what should you focus on? So what matters? Does it matter to have minimum skew? Does it matter to have minimum insertion delay? Does it matter to meet timing constraints? Or does it matter to insert a minimum number of buffers? And remember, these three were the points of classic CTS, but actually the thing that matters is this one. Okay, and we'll go back to the picture we saw before, and in CCOP the whole point was that we should focus really on the things that, we should take care of the things that matter and focus on the things that we can control and matter. That's what we should focus on. We shouldn't, focus on reducing skew, because skew doesn't matter. What matters is meeting timing constraints. No, skew is not completely independent of that. It means a lot, but what we should really do is try to focus on the things that really matter, which are meeting our max delay, our min delay, and our DRVs. And that's why what CCOP approach is to route our clock tree up to the clock sinks while fixing DRVs, buffering and so forth, but directly over to there. We call it clustering actually in the Cadence tools. So we get up to we route our clock tree, get up to the clock sinks, and once we've done that, now we can check timing. And when we check timing, we'll see, do we have any hold violations? Do we have new setup violations? If so, then we should go and start doing optimization by fixing them. And yes, touching the clock tree, adding skew in one place or another, adding buffers on the clock tree to fix that, which we don't usually like to do in classic CTS. Usually in classic CTS, what we like to do is build the clock tree and then try to add, delay buffers to fix hold and so forth on the signal paths. But with the CCOpt approach, you will play around with the clock tree until you really meet your timing constraints, not thinking about what your minimum skew is. That being said, the Cadence tool does take into account skew. It just gives it a lower type of of importance than classic CTS, which is zero skew balancing. Okay, question number 10. What happens to paths defined with set output delay after CTS? They benefit from positive skew. They suffer from negative skew. Nothing changes. The SDC inherently solves issues. We didn't discuss this issue in class. Well, we did discuss it. We even discussed it in a previous class on STA, maybe even in synthesis. But the answer is that they suffer from negative skew. And again, let's look at this now that we know a bit more about clock trees. So what happens is when we use this set input delay and set output delay type of an approach, which I said I don't like. I like using a set max delay type of approach. And the reason is this. We have our entire design, for reg to reg paths, which are the vast majority of our paths. We also, after CTS, we know exactly what this green delay is and what this red delay is, and we can figure out our skews, between these 2 points and really run our STA checks, and we have everything we need to know. The problem is these interfaces, these inter-reg paths and reg to out paths, and into out paths too, but they're just kind of like a specific case of, one of these inter-reg and reg to out. Okay, so what happens here is that we assume, we model that there's some sort of a virtual register out here that pushes that drives some sort of a delay, and we will say something like set input delay, and give it some number. And that is supposed to model the clock to Q and the delay of the logic until we get to this this port over here. And then we can go and look at what the length of our launch path is. And our capture path is from assuming that that register has a 0 on it, it has no insertion delay to it. Then we get the insertion delay to this, and that results in the fact that this clock is much later than this virtual clock, which is a 0, and we get positive skew on the input. Positive skew, as we can remember, it really helps our setup delay and hurts our hold delay. So we actually get this fake optimism on our setup delay on the inputs, and that's a really bad thing. On the outputs, the opposite thing happens. So again, in the beginning, we had 0 over here, and at our fake register over here, we had a 0. In fact, we used just some sort of a delay, like some sort of a logic cloud, to know what our launch path is from the register to the output. And the capture path, we had an ideal clock, so it was 0. Right? Now what we're going to do is we're going to build our CTS, so we have this delay that gets over here. Okay, and basically it means that the launch path became much longer, and it's going to be harder to meet setup delay, and it's going to be easier to meet hold. And again, these types of things are really bad. What the cadence tools do nowadays is they actually measure the average insertion delay to all of the flops in the design, take that average insertion delay, and they assume that the clock starts from minus that average insertion delay. And that is supposedly it's the same type of thing as giving some sort of an insertion delay to this modeled flop outside the chip. Is it the correct thing to do? I can't say. I don't think it's the correct thing to do, especially when you take a CC-op type of approach where you're going to have big differences in skew, in the insertion delay between one flop and another. What does the average insertion delay mean? I think the real way to do it is to set max delay to all, from inputs to registers, set max delay from registers to outputs, and know what you want to have here for your delay according to the top level design and so forth, and that's the way you should do it, and that will get you to the right thing independent of the inserting these the real propagated clock. So the answer is that they don't when we're talking about outputs, right? They don't benefit from positive skew; they suffer from negative skew. That's the answer to that question. Okay, question 11. Why do we shield clock nets? To reduce their power consumption, to ensure that they have enough space for routing, to increase their decoupling capacitance, or to make them less susceptible to noise. And what are we shielding them from? We're shielding them from noise. So it's to make them less susceptible to noise. So going back to that, what is a shield? So a shield is something like this. We have our clock net over here, and we take some sort of a constant net, be it VDD or ground, and put it around the net. Now, in this type of a picture, we put, some constant nets on the two sides, and we also put one on top and one on the bottom. In actual practice, we use Manhattan routing, which means we're going to have each layer of metal is going to be routed in a different direction, and they're going to be perpendicular to each other. What that means is that the actual area that we're going to have some sort of a cross between two adjacent metal layers in the vertical direction is going to be really small. We just have this little square here. So the coupling capacitance is probably not very big. Another thing is that the interlayer dioxide, it might be very big, so we might have a big distance. So I don't think in most cases we're going to route these top and bottom metal layers around our clock nets. In fact, it's really not going to be done that often. But what we often do, maybe even always do, is for our trunks, our big clock nets at the source of the clock tree, we're going to shield them on the sides. And that means we're going to take our clock net over here and we're going to run alongside it, a VDD or a ground wire that's going to shield it from any other types of signals that are going to be on the sides and possibly going to be making noise, that if that noise hits the clock signal, it's going to cause a glitch, and a glitch is going to be really catastrophic. It also shields the other signals from the clock, because remember, the clock has this really good transition, and that transition has high frequency harmonics, which are going to easily go through a capacitor and cause glitches on signals. But really, we want to mainly protect the clock tree. Now, the problem with that is that when we stick these guys on the side, it makes a lot of coupling capacitance or between these nets and the clock, and that's fine because these are constant nets. VDD and ground, they're not moving around, so that capacitance doesn't bother us in a dynamic type of well, at least on a noise, on a signal integrity type of way. But the problem is it adds capacitance that we have to charge and discharge during every toggle, so it's going to make things slow, and it's going to make things harder to get a good transition, and it's going to also make it waste a lot of power. So usually we're actually going to stick these shields at a double spacing or something like that to make sure that they shield any other signals that are running around in the chip, but also not cause such a huge increase of the capacitance of the net. Again, and that's why it's done at the the main trunks. It's not going to be done usually at the lower levels of the clock tree, because that would just take up too many routing resources and not enable us to finish routing our whole design. So the answer is, of course, not to reduce their power consumption, because the shields make the power consumption higher. It's not to ensure that they have enough space for routing, because the shields are going to take up a lot of our routing space. It's not to increase their decoupling capacitance, because decoupling capacitance is something that we do between VDD and ground. It has nothing to do with the clock, at least in this terminology. To make them less susceptible to noise, that's the reason we use shields. Question number 12. What is a DLL used for? Multiplying the frequency, implementing efficient clock gating, reducing the skew between parts of the chip, or creating a reference clock period. Well, a DLL is a delayed locked loop, and what it does, it reduces skew between parts of the chip. So let's go back to that, and we said that clock trees, clock meshes, and so forth are used to reduce the skew between the sinks. But one of the approaches that's very commonly used, and it was first shown by the Alpha EV7, also used by the Itanium, is to actually have local areas of low clock skew. So in this case, we had these local clock meshes on different parts of the chip, and we routed our clock to the middle of these areas, and had a clock mesh over here, which is an easier clock mesh to implement because it's on a smaller area. But then we get skew between these different clock meshes, and so what they do is they take a piece, they look at the sample, the clock over here on this mesh, and put it into a DLL, a delay locked loop, which changes the phase of the clock that goes into this area, and then we have a balanced clock between these two parts, etc. Another way to look at it is these de-skewing circuits, which is also basically a DLL that was used by Intel in the Itanium, and we had our PLL, driving the different areas that were then where they went through a DLL and into some sort of a clock grid that gave the actual clock signal to the flops. So that's something that can be done. The big difference between a DLL and a PLL is that a DLL, it fixes the phase of the clock. In other words, it removes the skew, but it does not multiply the frequency, and therefore it's not used as the main clock that goes into the design. We use a PLL for that because that multiplies the clock and gives us a much higher clock than our clock reference that's at a lower frequency outside the clock. Okay. And last but not least, question 13. What is the purpose of the circuit shown here? So, what do we see here? Do we see a 2-bit shift register? Do we see a clock divider? Do we see a synchronizer? Or do we see a FIFO? Well, anybody who's seen this before knows that it's a synchronizer. What is a synchronizer? So we saw that there's this problem of clock domain crossing. We will probably usually have more than one clock in our chip. So in this case, we have clock A and clock B. And because these clocks are asynchronous to each other, we don't know the skew between them. We don't know the phase between them. And since we don't know the phase, that's always going to cause, the worst case skew, and we'll never meet our max delay or our min delay constraints. So if you give the timing analyzer, two asynchronous clocks, a path between two asynchronous clocks, you're always going to have a worst case setup and a worst case hold violation. What is a path between two clocks? So this flip-flop is clocked by clock A. That means the signal that comes after it is synchronized to clock A. This flip-flop, on the other hand, is clocked by clock B. That means that the capture path is synchronized to clock B. That means we have a path between a flip-flop that's on clock A to a flip-flop that's on clock B, or logic that's on clock A to the capture signal that's on clock B. And that's a big no-no. We can't do that. Well, if we have by design, if we make it by design that it's okay that we're actually passing things between one clock and another clock, and we can't promise the timing between them, well, that could be okay. The problem is that we have this thing with metastability. So as we know, we're not allowed to sample a flop in its setup to hold window. So it has a timing window where we're not allowed to sample things. And because we don't know the phase between these two clocks, we're always, not always, once in a while, but that while is going to happen a lot when we're at a very high frequency, we're going to actually sample inside that forbidden window. When we sample inside the forbidden window, we do not know what happens on the output of the flop. In fact, we assume that we get a metastable state. Now, if you have a metastable state, something that's not a 1 or a 0, but somewhere between a 1 and a 0, there is a probability that that metastability will go and then propagate through the design downstream in the design after it and wreak havoc all over the place. Power consumption, but it can cause everything to go into unknown states and so forth. Metastability is a huge problem. So we never want a metastable state to be on this net at any time. So what do we do, and why does a synchronizer solve that? Because we can get a metastable state on this net over here. We will get it. We'll get it every once in a while. I don't know how long it'll be. There are all kinds of, calculations when you'll get metastability, but we'll get a metastable state, something in the middle. But the thing with a metastable state is, it's this hill, and we're on the hill, and we're right on the middle of the hill, and very soon, it will either fall down into one side of the hill or fall down to the other side of the hill. We do not stay in the metastable state for a large amount of time. And if we have enough time until we're going to sample it, which is the clock period of clock B, because clock B, sampled the metastable state on the first rising edge, it's going to wait a whole clock period until it samples this guy over here. We're going to meet setup and hold of the second flop. And then we get a non-metastable state that's going to go over here. Now there is a question that I want to ask you. Which state is it of this? The previous state or the next state? And the answer is we don't know. It could be that, the metastable state, or when exactly this clock rose, sampled the previous state, and it may have already sampled the next state. That's because we're in this, setup and hold window that we're not allowed to sample at. So it's going to do one of them. And that is going to the next cycle propagate out into here. So we have to build our logic that talks between, the flip-flop over here and the logic down here, to the point where it's not going to be sensitive to that one cycle that may be lost or may not be lost. So, but this will the synchronizer is the main way that we can solve metastability problems between two at a clock domain crossing, as long as our design is built to enable such a non-clear value that's going to be going downstream in a certain clock cycle. Okay. That being said, there are other ways to solve clock domain crossing, such as using FIFOs. But that is one thing. This type of circuit is used sometimes for really worried companies. They'll actually have 3 flip-flops to reduce the mean time between failure, because there is some sort of very, very, very small probability that the signal that goes out over here is also going to be metastable, or that the metastability doesn't subside within one clock cycle, especially if you're at a really high clock cycle. But usually, it's generally only 2 flip-flops are used. By the way, you're going to have a false path between this signal and the clock going over here. So, or else your STA is going to fail on that. But this clock signal is fine because it's going through a synchronizer. And synchronizer are often provided in the library as a single cell. So you'll get a cell that already has these two flip-flops in order not to cause skew between, and the clock net over here. If you just instantiate two flip-flops in your design, which is something that's commonly done like in RTL, then you're going to route to these guys, and you might actually get a hold violation between these two guys, which is not something that you want either. So the answer, it looks like a 2-bit shift register. In fact, it is a 2-bit shift register, but not in this context. Is it a clock divider? It also looks kind of like a clock divider, but it's not a clock divider exactly. Is it a FIFO? No, it is not a FIFO. A FIFO is more complicated than that. It is a synchronizer. So that was our Lecture 8 Kahoot. I hope that helped you out. It was a pretty long one. It's a long lecture. But if you have any questions, you're always able to ask me on my YouTube channel.